we're going to count. We're going to start from 0. You ready? 0, 1, 2, 3, 4. Keep counting and go forever. And that is the set of natural numbers. So what's in there? Well, I know you've heard of even numbers or odd numbers, and maybe you've heard of prime or square numbers. Today, we're going to talk about some natural numbers that are really weird. So the cool thing is that at first glance, you probably won't even recognize these as numbers. I'm Heidi, and welcome to Wild Things. All of the natural numbers are written down as strings.
A string is just a bunch of symbols arranged in a sequence. Here's the set of symbols we use to write numbers. The set of allowed symbols is called an alphabet. By arranging these symbols in different orders, we can create all of the natural numbers. Words are also strings. And here's an alphabet for words. Using this alphabet, we can make all kinds of words. We can also make strings that aren't words. Let's add a period and a space to our alphabet. Okay, now we can make sentences, and sentences are strings. If we let our keyboard be an alphabet, then a book just becomes one big long string. And we can put that book in a library that is full of strings. Your DNA is a long string with an alphabet made of nucleotides. Cytosine, adenine, guanine, thymine. The symbols of a string don't have to be written with pen and paper. They can be written with molecules. A sweater is just a series of stitches. In this case, the pattern is knit, knit, purl, purl, and then you repeat. That's a string. Computers have an alphabet of electrical signals, on and off. But people usually just write 1 for on and 0 for off. Everything inside your computer is a string of zeros and ones. Your emails, your pictures, your text messages.
This video that you're watching right now that's streaming across the internet to you is just a big string of zeros and ones. So strings are all around us, and they're written in all different kinds of alphabets, and you're going to find them any place you find data or information. But did you know that all strings are numbers? Well, more precisely, all strings can be interpreted as numbers. So before we go any further, we have to take a moment to talk about how we write numbers down. Now, I hear you've been studying exploding dots, so you'll recognize this as a 2-to-1 machine. Now, if you haven't seen exploding dots, I'm going to give you 2 websites. The first is www.gooddaymath.com, and the second is www.explodingdots.org. I'll put these both in the description below. These sites have James Tanton's Exploding Dots, and it's totally amazing, and it will blow your mind, and it will change the way you think about numbers. So back to that 2-to-1 machine. So we saw that in a 2-to-1 machine, we can represent all of the natural numbers with just an alphabet with 2 symbols, 0 and 1. Then we made a 3-to-1 machine, and we represented the natural numbers with just an alphabet of 3 symbols, 0, 1, and 2. So then finally, we made a 10-to-1 machine, and we represented all of the natural numbers with 10 symbols. Of course, these are the standard symbols that we're used to using. But the point here is that there's nothing special about the size of the alphabet that we use to represent numbers. We could use 10 symbols, we could use 2. If we wanted, we could use 26, or we could use 117. It doesn't matter. Also, there's nothing special about these symbols. If I wanted, I could replace them with my favorite emojis, and I could still do math. It just would look a little different. Okay, so here's the thing it's so cool about strings. All strings are secretly numbers, okay? So here's the word cat, and I'm going to show you how it's secretly a number, right? Here's our alphabet, 26 letters, right? Let's make a 26 to 1 machine, okay? And then let's figure out what number this word is. So the first box is the ones column, or the ones box, and then we have the 26 box, and we have the 26 squared box, right? So we'll start with the symbol C, okay? So C has a value of 2, so I'm going to put 2 dots in this box. Now let's add up and see what that is, right? So we have 2 times 26 squared, which gives us 1,352. Now let's move on to the contribution of the A. Now the A is a 0, so I don't have to put any dots in that box, right? So 0 times 26 is just 0. Okay. Now the letter T. Now T has a value of 19, so I'm going to put 19 dots in that box. So 19 times 1, well that's 19. When I add it all up, this word, cat, is secretly the number 1,371. Very cool, right? So now we're going to get even crazier. So here we have an email from my mom. Now it's definitely a string, but what I'm saying is that it's also secretly a number. We could do the same trick we did before. I could take all the symbols that are used in this alphabet, count them up, let that be the base, and then I could go through each symbol and figure out what this number is. I can tell you it would be a really, really big number. But I don't even have to do that because when my mom typed this into her keyboard, the computer turned it into a big, long string of zeros and ones. And of course, from exploding dots, we know that any big, long string of zeros and ones is just a number. So here's the thing that's strange about it. My mom, she didn't mean to send me a number. You know, she thought she was sending me a recipe for root beer cake. But the computer sent it as a number. Here's one of my favorite examples. This is a computer program that I wrote. So it's definitely a string. But when it gets written down on my computer to be run by the computer, it's written as a big long string of zeros and ones. So it is a program, but it's also a number. So the other thing that we can do with this program is we can run it. And when I run it, it generates these numbers, which are the prime numbers. So what's cool about this particular string is I'm going to give you 3 ways of interpreting it. It's a string that represents a program. It's also a number. But in addition to that, it's also a set of numbers. So this string has multiple interpretations. So strings are everywhere, and all strings are numbers. But most of these strings were not intended to be numbers. So an interesting question is, are these numbers sort of random or arbitrary? Well, here's one way to think about it. On the right, I've generated a bunch of random numbers, and I want to put on the left a set of numbers that isn't random. So I'm going to pick the prime numbers. And the question is, are our hidden string numbers more like the numbers on the right or the numbers on the left? Well, what's the difference really? The set of random numbers has no shared or unifying property. There's no relationship to tie all the elements together, and that makes random numbers hard to describe concisely. So if you had a set of, say, 1,000,000 random numbers, how could you write it down in a way that is concise, but that would allow somebody else to recreate the set exactly. Well, if your numbers are random and they don't have any unifying property, the best you're going to be able to do is just write the whole set down. And that's not very concise, but that's the essence of random. So prime numbers share the property of being prime, and this makes it easy to represent them concisely. Instead of writing down every single number, I can just tell you the shared property. I can describe every single prime number with this one relatively short string.
It's sort of a cryptic string, but we're going to take the time to translate it into English. A prime number x is a number that's greater than or equal to 2. And if some other number y is a factor of x, then that number has to be either 1 or the number x itself. And that's the standard definition of prime that we're familiar with. A prime number is any number whose only factors are 1 and itself. Now, there's two things I want to point out about this definition. First, it's a short, concise way to describe an infinite set of numbers. And second, it's a mathematical description. In addition to the basic logic parts of the statement, we use the concept of equals, greater than or equal to, and we use multiplication. That's it. Prime can be defined with the concepts of grade school arithmetic.
So if we take a bunch of strings and we interpret them as numbers, do those numbers all share a property? And is it a mathematical property that we can describe with arithmetic? Well, next I'm going to tell you a story where exactly that happens. Our story begins with a mathematician named David Hilbert. Now, Hilbert wanted to make a proof system for all of mathematics. Now, Hilbert didn't build the system himself. Lots of mathematicians contributed, like Bertrand Russell, Alfred North Whitehead, and Gottlob Frege, just to name a few. So what's a proof? We all have a pretty good informal idea of what a proof is. You make a series of arguments or statements, and you finish with the statement you're trying to prove.
The cookies were in the cupboard when I left for a walk. You noticed the cookies were eaten at 2 p.m. I got home at 2:15, therefore I didn't eat the cookies.
But what's an argument? And how do you know that one statement leads to another? How do you know that your proof is correct? We can make our proofs more formal. And if you've taken a geometry class, you've probably had to write a proof.
And it also included a series of statements. But you may have been asked to provide a reason for every statement. Now, a reason was often a definition or a theorem from your book.
And these justifications force you to be more clear and more precise in your reasoning. And it also meant that somebody reading your proof could go look up those theorems and definitions and check each statement to be sure it was correct. Hilbert's crew wanted to be even more precise and formal.
In their system, a proof was also a sequence of statements. But they had very precise rules about how new statements could be made from old statements. And the rules were so precise that they could be checked by a machine. And this made sure that the proofs were free of errors.
So inside the proof system for all of mathematics was a smaller proof system for the natural numbers and arithmetic. So that means addition and multiplication. Now this part of the proof system was very important because all of the other parts of the system were dependent upon it. So we know what the natural numbers are. Let's pretend that they live in this great big oval. And we know there's lots of subsets of the natural numbers, like prime or divisible by 3. And they all live inside this big oval too. The big pink arrow represents the relationship between the proof system and the natural numbers. So proofs are things that we write to prove things about the numbers. And the two things existed separate from each other. Now let's look at the inside of the proof system. What did the proofs look like? So here's a proof. It's a little hard on the eyes, but remember, these proofs weren't intended to be read by people. They were intended to be read by machines. This happens to be a proof that addition is associative, but that's not important right now. The important thing is that this is definitely a string, so it's also a number. In fact, it looks a little similar to a string we looked at earlier.
Remember that cryptic string that defined the prime numbers? That's also a statement in the proof system.
So next, along comes another mathematician named Kurt Gödel.
And he took a look at the proofs in this proof system. But instead of seeing proofs, Gödel saw numbers. So he gave the system just a little push till it landed inside the natural numbers, where it belonged. So next, Gödel wrote a mathematical definition of all his proof numbers. It was pretty long, so you have to imagine it going way off to the right. But as long as it was finite, which is a very concise way to describe the infinite set of all proof numbers. And the amazing thing is that it was a mathematical definition. It used equals, greater than or equal to, multiplication, and it also used addition, but we don't have that part on the screen. You can even see the definition of prime embedded inside it, as were other mathematical properties like power of or divisible by.
So let's just review for a minute. If you take proofs and you interpret them as numbers, you don't get just random arbitrary numbers. You get numbers that all share the same mathematical property, and it's the property of being a proof, which is the coolest thing of all, that the property of being a proof is just this complicated, fancy property that's built up from arithmetic, multiplication, and addition.
The process of building a proof is inherently mathematical. They made their proof system so formal and so precise that they turned it into arithmetic.
So the proof system lived inside the natural numbers, but it was still a proof system, so Gödel started writing some proofs. He could have written proofs about prime numbers, or numbers divisible by 3, but instead he wrote proofs about proof numbers, which he could do because he had defined his proof numbers within the system. So he used the proof system to write proofs about proofs, which is like the proverbial snake eating its own tail. So that's all we have time for today. But before we go, I want to give you a little glimpse of what's coming next. So Gödel showed that if your proof system lives inside the set of things that you're trying to prove things about, well, then you can make all these crazy recursive statements. And you end up with statements that are true, but they can't be proven. And this is true in any system for the natural numbers in arithmetic is going to have this problem. And that was a shocking setback for Team Hilbert and their goal of trying to build a proof system for everything. But on a more practical note, the root beer cake my mom sent me was sort of a disappointment. I didn't care for it. So
It's something with your cake.
it's not root beer cake, it's chocolate cake. Hi Goldfish. This is my favorite chocolate cake and it's delicious. Thanks for watching.